presenter is Tara Lindsley, and she's a professor at Albany Medical College. And she's going to show us a virtual brain model learning resource using open source software.
Thanks. I apologize for my laryngitis. I don't usually have such a Hollywood voice. So at Albany Med, I co-direct the first year medical student course in neuroanatomy. And about 4 years ago, I worked with a team of students and faculty to develop a new learning resource for that course. And it's called the Albany Medical College Virtual Brain Model Software. Of course, students will never call it that. I don't call it that anymore either. It's the VBM, affectionately called VBM software. And this is a unique electronic library of human brain anatomy that was developed in large part using open source software. And although it's been available for free download from the AMC website for about 3 years, and although we are getting very regularly now emails from users all over the world to include not only medical students, but high school students and their teachers, undergrads and paramedical professional students and their teachers. So I wouldn't exactly call it viral, but we're really very satisfied that people are finding out about the program and using it. We also have been conducting a study to measure the effectiveness of the learning tool in the medical school setting. How are students using the tool? How effective is it compared to more traditional resources? Since I don't have very much time to talk to you about the tool today, and given the focus of this festival, I thought I would spend the time that I have just talking primarily about how the open source software was instrumental in making it possible for us to develop this resource. So by the end of this session, you should be able to especially understand how we used open source software, something about the capabilities of the software itself, its functionality, and how we're using it in the setting of neuroanatomy education at the medical school. And of course, hopefully you'll be able to download it and try it yourself. Now, this is a quote from Jerry Edelman, who really captured the essence of the relationship between brain structure and brain function. He said, perhaps the most important general observation that can be made about the brain is that its anatomy is the most important thing about it. And I would tend to agree, simply because, frankly, the brain structure-function relationship explains a whole lot about what might seem illogical at first. So, for example, I should tell you that brain anatomy and learning neuroanatomy at the medical school is considered one of the most difficult in first-year medical school curriculum, and that students have coined the term neurophobia to describe their dread of the course. But it's a fair thing to say that the anatomy of the brain is somewhat uniquely complex in the human body because it's a mush, it's all pretty much the same color, and the structures that have very different functions can coexist in very close relationship to each other spatially. And a lot of those structures that are very important for brain function are not visible from the surface of the brain. And so our brains are not see-through. We don't have X-ray vision, much as we'd like our students to have it. And so we have this problem where students, to achieve an understanding of the spatial relationships of the brain, they have to develop a kind of mental map in 3 dimensions of various brain structures that have quite different functions. And so I'll use an example from our previous speaker that I was thinking about listening. So if you have a patient who comes to the emergency room and they've been attacked by a turtle, and this has damaged their nervous system, you could, if that lesion, that damage occurred in a particular spot that I know because I know the neuroanatomy, that patient could present with deficits in function that are combined, that are the left side of the body could have a motor dysfunction, the right side of the body could have a sensory dysfunction but no motor dysfunction, and one pupil can be constricted. All because of one small localization. Another patient, for example, small tumor the size of a pea in a particular location could cause a combination of deficits of infertility, abnormal bone growth, and double vision. So you begin to see how it's a solve this problem. Here are the clues. Where in the nervous system do these structures coexist close enough together that a vascular accident would hit them all, or a tumor could be damaging them all? So this is the task. And since most clinical deficits in some way or another reflect those spatial relationships, our students have to learn the neuroanatomy. And it's not just neurologists that have to know neuroanatomy, because about a third of all long-term disabilities are neurologic in nature or psychiatric in nature, and about 20% of adult hospital admissions are neurological problems. Okay, so even your family doc has to recognize a neurologic problem when they see it. Unfortunately for students and for educators, as I said, the brain anatomy is incredibly complex, and a lot of important structures can't be viewed from the surface. So this is the old school way that students learned neuroanatomy. You take human material, cadaver material, and you dissect it, and you try to find various structures of importance, and you use at the same time maybe a plastic model that has different pieces you can pull apart. I don't know how many of you took organic chemistry. Remember the models you could build? They're solid models. We have print atlases. These are essentially serial sections of the human nervous system that have been stained to visualize certain nuclei, certain tracts. And we do have 2D medical images like MRIs and angiograms, CAT scans, etc. But it's still up to the learner to put it all together in a mental map and to recognize these spatial relationships. Some students are very good at it. My neurosurgeon husband back there is very good at this. He can find his way anywhere in Albany. He's got that spatial thing that some people have. I do not have it. I still get lost. I've been living in Albany for 20 years. But I know my way around the nervous system, and it's because I spent years with these traditional resources. But I feel the students' pain when they say, I just don't get it, Dr. Lindsley, help me out. And so we started, the faculty, and some of these students who were struggling started saying, if we could design the perfect learning tool for this particular struggle, what would it look like? Well, it would be flexible. That is, the user, the learner, would select the structures to view. Now, some structures, you know where they are, you know how they're related, and some are a little harder to picture in space. You want to be able to view it from all different kinds of perspectives, like you would hold a plastic model in your hand and rotate it around, look at it from underneath, look at it from the side, etc. You want to be able to zoom in, zoom out, so you can see just the close neighbors or the whole brain in context. And you want to be able to see through that surface, so the relationship of surface structures to deeper structures is more obvious visually. Now, I, as an educator, also needed a few things on the wish list. I wanted to be able to have that list of structures the user could look at be the same ones that are important in our curriculum. So as many of those important structures that have functional relevance for clinical problems as we could, we wanted in that. And that included some certain pathways where the brain, one region of the brain talks to another. We also wanted it to ideally have clinical images, the kind that students would be encountering in a clinical setting. So the MRI standard views, planes of section was important. And honestly, not very many techies in the medical school, I have to say, especially among the faculty. So it had to be easy to use, easy to learn, not a lot of time investment to be able to jump in and use this model system. Now, it seemed impossible to us 4 years ago that somebody hadn't already done this. There were so many 3D rendering programs out there, many of them open source, and so we went on a hunt. This was what we were looking for. We had a wish list, and we searched. I think 3 or 4 of us spent months searching online. This is a very short list of some of the really nice sites we found, but we looked at hundreds of web-based atlases and animations, but so many of them had some of the features we wanted, but not all of them. In particular, some of the animations were beautiful. You could run your mouse along a slider and cause the brain to turn around, but you couldn't select what structures you wanted to look at, or the turning was limited to what was already programmed in that animation. There was no flexibility. And so, bottom line, it didn't exist at that time, and we couldn't, or if it did, we could not find it. So we decided to make one of our own, which really was completely completely naive looking back on it now. But we had a student with us who really believed he could do this, and he was highly motivated. He had the whole summer between first and second year, and we had work-study money to pay him, and he worked full-time on this. So we started by generating serial sections of medical images using an MRI. We worked with the GE Global Research Group that has a Neurosciences Institute at Albany Med, and they did high-resolution imaging with their 3T magnet, their 3 Tesla magnet. And so these are some of the individuals that helped us with this. And this MRI scanner generates DICOM files, and we use the GE DICOM reader for Internet Explorer to manage that. And we had a volunteer. It wasn't Homer Simpson, but in fact, our healthy volunteer was that highly motivated medical student, Joe Roselle. And so he gave consent, we scanned him, and we had very nice MRIs. Now, I don't have time, and I'm not sure you really want to know all of the physics associated with what an MRI is, but suffice it to say that magnetic resonance images are not X-rays. They're digital maps, spatial maps, of what's called relaxation energy. And all the tissues in your body have a certain unique relaxation energy. And that energy is released after you put the tissue in a very powerful magnet. And the protons in that tissue will align with the magnet, much like iron filings on a magnet that you would hold in your hand. And then you pulse a radio frequency, and that causes all those protons to go randomly in all different directions and out of alignment with the magnetic field. And then you record the relaxation energy as they realign with the field when you take the pulse away. Basically what you end up with is images, that is tomograms or slices in serial section through the tissue, in this case the head. Axial plane would be sort of the horizontal plane from top to bottom. Sagittal plane is from left to right. And the coronal plane is from front to back. And those are the standard 3 serial planes that typical MRI is obtained in. Now within those images, of course, these are digital images, so they're made up of pixels, and they have a volume, so there's a voxel associated with them. Even the highest resolution MRI, and of course the one that we used at the time was very high resolution MRI, still has a limited ability to resolve 2 separate structures to a degree less than a few millimeters. Unfortunately, a lot of really important structures in the brain are less than a few millimeters thick. And so you can see a lot with an MRI about the structure of the brain, but not as much as we need our doctors to know. So it was pretty good. It also, just the last thing I want to point out is this little point at the end, that a typical MRI of the human head has 326 axial slices, digital 2D images of slices through in this plane, 248 sagittal, and 300 coronal slices. That makes about 24 million pixels. Lots of data. So we took all that data in serial section and we searched, and actually we kind of found the software first, but basically what we did next, to step 2, was to create a database, an image database that would allow us to render the structures of interest within Joe's brain in 3 dimensions, in a virtual 3D model, kind of like a plastic model, only on your computer. And we found and used what's called ITK Snap, which is just one in a toolbox or toolkit generated by the Insight Segmentation and Registration Toolkit people. This is an open source software system developed by 6 organizations, one of which was Kitware. 3 of these organizations were corporate and 3 were educational. The applications were actually originally developed for the National Library of Medicine's Visible Human project. And I can tell you more about the funding if you're interested, but I don't want to run out of time to show you how the model works. So let me just say that just one of the tools in this toolkit was ITK Snap. And it's a piece of software specifically designed to take medical images in serial section like MRIs and to delineate, that is to identify certain structures and extract those structures for rendering in 3D. Open source, and the websites are there if you're interested in learning more about them.